Good evening, everyone. My name is Jyoti Sharma, and I will be taking this live session for 2 hours from 6 to 8 p.m. This is actually second last week where I will be taking this live course, and the course name is Environmental Quality Monitoring and Analysis. This is my brief introduction that right now I'm a PhD student from ISO Bhopal. I did my MSc from FRI Dehradun and my undergraduation was from Delhi University. I already have cleared UGC GRF net and ICER net and because right now I'm a PMRF research fellow. That's why I have a responsibility to teach. And based on that, I also have some relevant NPTEL experience also. For example, for air pollution and control, environmental chemistry, and microbiology, basic environmental engineering, and pollution abatement. So, along with this introduction, I come to how I will proceed the course. So again, I will have a lot of MCQ questions. Four options will be given, and you are highly encouraged to answer the right option. Please don't worry if you are thinking that if you are hesitant. So please speak up because that's the best way to interact. Then I will not go to week 1 to week 8 content because we already have explained a lot what we have covered from week 1 to week 8. But the important part here is right now we are on week 12, but the content of the week 12 started in week 9. So in week 9 we started with interface mass transfer, and in which we talked about the fluxes. So the flux depend not only on diffusion but also depend on the advection term. So and whenever we are moving from one phase to another phase. So, for example, if a contaminant is moving from water to air, then there is very thin film that is known as the interface film. So, this here at the interface, there is a resistance. So, in week 9, we started with an equation that calculated the resistance at the interface, and so and resistance in the water side, resistance to the air side. So we tried to learn to calculate the resistance at the both sides, right? So this is what we learned in week 9. In week 10 we started with the example. So in week 9 it was just the concept. In week 10 we started to take an example. So for example, it is water to air, air to water. If something is moving, then what kind of flux there will be, what kind of resistance there will be. So we started with that, and we touched sediment water exchange. This is very important because whenever there is any kind of oil spill, uh, whenever there is any kind of oil spill, then that will go to the sediment, and above that we have the water. So there is a sediment water exchange that we will learn. Deepa asked me the question, any information about the hall ticket? When will they give the hall ticket, since the exam is on 17th April? Actually, Deepa, I am not aware of when the people will give the. I think you can mail them because I'm not aware when they will give this. Yeah, when they will give you information about the hall ticket. Okay. So in week 11, we completely talked about the sediments. As I told you, but the interesting part of the sediment is that sediment have the solid part as well as the pore water sediment has. And that's why if contaminant is on the solid part, it may be that it interact with the pore water, and then it will go to the water. So that's how it creates the complexity that we learned in week 11. And so in week 12 what we will learn about the other mechanism of chemical release from the sediment concepts. For example, resuspension, we will learn about this. And Attenuation, we will learn about this mechanism also. Advection, there may be some advection, we will learn about this. Soil air transfer, because still now we touched air water and sediment water, but we need to learn also about this soil air transfer. And then some remediation of the contaminant sediment. So if we have any sediment under the water, and that sediment is contaminated, then how we can treat it? We can let it as it is, or we can use some remediation technology by which we can remove the contamination from that sediment. So we have a lot of techniques by which we can remediate the contaminate sediments. So we have few questions left for the week 11, so we will first cover these questions and then we will go to the week 12 content. The last session will be on 14th, so this is on Tuesday. That will be extra class, so I will try to summarize all the course. And yeah, so that will be the last class. Okay, so I start with the question only. So my first question is, in the semi-infinite sediment model, the boundary layer rho a2 is equal to rho a20 at z, that is approaching the infinity, where rho a2 is pore water concentration and rho a20 is initial concentration, is used because I have four options here. Diffusion is zero at large depth. Uh, Adsorption vanishes far from the interface. The far region remain unaffected during the time of analysis. Pore water must equal bulk water. So let me just explain to you. So for example, this is our interface, and here we have sediments. Here we have sediments, and here z is equal to 0. So if we are going away from this, so let's say this is z is equal to or approaching the infinity. So here, what we are saying is that here we have the concentration of A. 2 means in the pore water. So in the pore water, we have pore water concentration, and then rho A20 is the initial concentration that we actually have. So we have two things, rho A2 and rho A2 node. So you have to tell me why these are equal to each other when uh, z is approaching the infinity. So what we are saying in the question is that if we are uh, going away from the interface, so z approaching the infinity, then why the concentration of A in the pore size is equal to the concentration of A in the pore size at the initial time? Because initially, so let's say initially our concentration is rho a12 node, right? Initial our concentration of A in the pore size is rho A2 node, but because Z is away, so let's say if it is a 500-meter away from the interface or 1 kilometer away from the interface, it means, and what we learned, that we have a assumption uh, that we have the equilibrium condition, or that every place. So if z initially, from z0 to z infinity, we have uniform concentration, right? We do have uniform concentration of A in the pore size. This is what we are, we have the assumption to simplify our equations. Okay, then what will happen at the interface? And yeah, so if it is a uniform, initially it is rho A2 0. Okay, at the interface where z is equal to 0, the concentration of rho A2 will be changing, because it is the function of time, because some of the concentration of A will surpass and will cross the boundary. Okay, and there will be less concentration of your A, but it is near to z is equal to 0. Okay, but what we are saying is that our condition is when z is approaching the infinity. So it means here there is no any deficit of the concentration. There is no any deficit. So initially, whatever concentration of A we had, this will be the same at z approaching the infinity. So the thing is, uh, even if your concentration of contaminant A is function of time t, but if we are saying that our z is approaching the infinity, it means that particular area is not affected till, because of this time, and whatever initial concentration we had of that contaminant A, that will be same as z approaching the infinity. So C answer is the right one. So z approaching the infinity is the far reason that will remain unaffected during the time of analysis, because the affective reason will be near to the infinity, and you know that diffusion is very slow. It means no doubt some of your concentration of A will move to the interface, but because we are saying that our z is approaching the infinity, it means during the time of analysis at z approaching the infinity, the concentration will be same, is not changing with the time. Okay, so that's how C is the right answer. So what we are saying is that this is different way of explaining the things, but just see that even though time is passing, diffusion only penetrate up to a depth. Beyond that, sedimentation is unaware of any change. So what I said is, near to the interface, there will be the change in the concentration of A in the pore water, but what we are talking is very far away from the interface. So, and because diffusion is very slow, so what we are assuming that at z, that is approaching infinity, the concentration will be same as it was initial. Okay, so the interface condition, capital Ka23, in bracket we have rho A2, where z is equal to 0 minus rho A2 infinity is equal to minus d A32 delta rho A2 by dz, and here z is equal to 0, represent what physical situation? So I have four options here. Diffusion and convection occur in sediment only. Diffusion flux equal convective removal at the interface. Surface concentration is constant. Water size transport is always slower. So again, I'm drawing the same thing. So this is the interface, and here we have sediments, and on the sediments and even in the pore size, we have A, the contaminant, and this is your water. So, and here z is equal to 0. Sorry, 0. So, this A has to be transferred through this interface and have to reach to the water where we do not have the sediment. Okay. And then, okay, so the hint that I'm giving right now is that the sediment, here in the sediment, the movement is due to diffusion, right? The movement is due to the diffusion. So if you have A is present on the solid, and A is also present in the pore size, pore water, right? And it will move through the diffusion only. Okay. But here, if it will cross the interface, here A moment will be due to advection, right? So now you have to tell me this equation is representing what? So, okay, uh, let me tell you. Here, this is diffusivity, right? This is diffusivity. This is change in your concentration of A in pore size with the distance z. So let's say this is z is equal to 0, and here there is z is equal to, let's say, some z dash. So with the distance, there is some gradient of your concentration of pollutant A. Okay. So, and this is diffusivity. So what we are saying is this is your sediment side thing. This is your sediment side thing. And you know that whenever we have diffusivity and we have this gradient multiplied by the gradient, this is giving us the flux. So this right hand side term is nothing but the flux at the sediment side. Okay, so it is something that with something z crossing the z distance, there will be the change in concentration of A, and that's how it will diffuse. And this diffuse is also depend on the diffusivity, and which is here shown as the Da32. So it means whenever your A will come to this interface and will cross this part, this is just due to the diffusion, and the flux is represented by this right hand side term. Okay, now coming to the left hand side term, this K is your mass transfer coefficient, and just see here, this is 2 3, so this is water side. Okay, this is water side, and what it is saying that we have rho A2 at z is equal to 0. So here we have some concentration of A that we have in the pore size at the pore water at the interface, minus rho A2 infinity. So rho A2 infinity means here at the bulk. So here we have concentration of A in the water at infinity, or away from your sediment. Or so this is your bulk water gradient that is being created. At the surface, we will have more concentration of A, but because it is moving from up from bottom to up, so what we are assuming is that a concentration of A in the water, uh, which is defined by rho A to infinity, is 0, mostly 0. So we can also neglect this term, but what we are saying here is that, and this is your convection, right? This is your convective term. So what we are saying is that whatever is coming from the sediment side is taken up by the water side and it is removed. Because, and if we are saying that it is equal, then it means there is no any accumulation. Okay, so flux is equal, flux at the sediment side and at the water side is equal. So here B answer will be the right one, that diffusive terms equals convective removal at the interface. Two things that you have to keep in your mind. The first is, if it is moving from the sediment, so it will be, there will be diffusion. Whenever it will cross that interface, cross that film, then there will be the convective term that will be more dominating. And because what we are assuming is that there is no any accumulation, so if there is no any accumulation, then diffusive flux will be equal to your convective flux. And this is what is showing in this statement or in this equation. So that's how B answer will be the right one. If you have any problem, you can just let me know. Another, otherwise we can move. So again, I'm giving you the explanation in the words. So we have rho A2 Z is equal to 0. So this is the concentration of species A in phase 2, that is pore size, that is evaluated at Z is equal to 0. So this is your interface, at the interface. Rho A2 infinity is concentration of A in phase 2 in bulk water. So this is your interface. So here you have bulk water. So bulk water away from the interface, away from the interface. So that's why we are saying that this is infinity rho A2, and we can assume is equal to 0, right? Then we have Ka23, that is mass transfer coefficient of species A from phase 2 from interface into the bulk water. And this is the gradient, and then gradient and this diffusion coefficient is giving you the diffusive flux. Right, so this is your diffusive flux. If we are talking about this left hand side, so left hand side is this one. K is equal to your water side mass transfer coefficient. Rho A2 Z is equal to 0 is concentration at the interface. Rho A2 infinity is concentration in the bulk water. And this represent flux from interface to water, right? If we are talking about the right hand side, so we have this diffusion coefficient, we have this concentration gradient that is at the interface, and what this is representing is the flux coming from sediment by diffusion. And because we are equating them, so the physical meaning of this is nothing but this is the diffusive flux from the sediment is equal to convective removal into water. So there is no any accumulation at the interface. So whatever is coming at the interface by diffusion is removal by the convective flux by the water. So this is what is represented by that particular equation. Okay. The next question is, even though capital K A23 is constant, why does flux decrease with time t? Surface concentration decreases due to depletion and diffusion from depth. Diffusion coefficient decreases with time. Porosity becomes 0. Background concentration increases. What it is saying that you know that this is your mass transfer coefficient in the water side, and that is the part of your convective, sorry, not advective, this is part of your convective flux, right? So what it is saying that even if this convective flux mass transfer coefficient is constant, how flux can decrease with time t? So we have four options here. Surface concentration decreases due to depletion and diffusion from depth. Diffusion coefficient decreases with time. Porosity becomes 0. Background concentration increases. How flux can decrease with the time? Again, I'm drawing the same thing. we have the interface. Here we have sediment part, and here we have water part, water side. And A is moving from sediment to water, and we need to cross this interface in the water side and in the sediment side, right? And even if here capital K A23 is constant, even then the flux is decreasing with time. Why? The simple answer is that your surface concentration decreases due to depletion and diffusion from depth. The first thing that you need to make strong into your mind is that diffusion is slow. Diffusion is slow. We all know that diffusion is slow, and diffusion is dominating in the sediment side, right? So here, if this A is moving to this interface, it is just due to diffusion, right? Initially, we had the concentration rho A, um rho A2 node at the interface. Okay, because what we are assuming is this is equal in all the sediment initially. Okay, then what will happen? Some of your concentration of A from the pore side will go to the interface, will cross the interface, and will go to the water. So here, near to the interface, near to the interface, the concentration of your A will be decreased, because the concentration that we have here at z is equal to infinity has to go near to the surface or near to the interface. And because it is slow process, that this means there will be some depletion. There may be some depletion, because from the interface, the concentration A is being removed, but it has to be taken. So the concentration should come from the bottom and should be equal at the interface, so that it can again remove. But because diffusion is slow, so what we are saying is that because the diffusion is slow, it means uh, the the replacement is slow. Okay, because at the interface A will be removed, then this A has to be replaced from the bottom. And if your diffusion is slow, then what we can assume is that there will be the diffusion, or sorry, the transfer of this A to the bulk water will be very slow, because here the concentration is now low, because it can't replace completely well on the time. So it means whenever we will have more time and more time, so your diffusion will be decreased, just because the depletion is not fulfilled by the replacement from the bottom. So yeah, A is the right answer. And if I show you in the equation, so this is your Ka23, that is constant, and your flux now depend on this one and this one, right? So if we are talking about this one, your concentration of A in the pore size at interface is equal to 0. Okay. So over the time, chemical is continuously leaving the interface into water. So surface concentrations start decreasing. At the same time, deeper sediment try to replenish it by the diffusion, but diffusion is slow. And that's why there will be some depletion that will occur near to the surface, and supply is weaker with the time. So that's how the concentration gradient will reduce, and the flux will also reduced. So Just the blame that you can put is on the diffusion process is very slow. If some concentration is removing from the interface, there should be some concentration that should move to that place, but moving from bottom to up is very slow process, and that's how uh, your flux will be decreased. Okay. Now the question is the boundary condition rho A2. So this is the concentration of A in the pore size where Z is equal to 0 and there is some time at some time t is equal to 0. So what we are saying that your surface concentration assumed to be 0 implies what? Sediment initially has no contaminant, adsorption is negligible, convective is much faster than diffusion, diffusion coefficient is 0. So this question is more about the mathematical representation rather than the concept. So what it is saying that we have concentration of A in the pore water at place where z is equal to 0, so it means at the interface and at some time t, and if we are saying that this concentration is equal to 0, so surface concentration that is assumed to be 0 implies what? So here, what we can say is that convective is much faster than diffusion, and let me explain it why. So till now, what we have learned is that, again, I'm drawing the same. So this is sediment and this is water, and your A is moving from sediment to water. So there is some flux at the sediment side and at the water side, and because there is no any accumulation, so what we are saying that flux at the sediment side will be equal to the flux at the water side. And what we have learned is that flux in the sediment side is due to diffusion and flux in the water side is due to your convective flow, right? So what we have learned, now I'm writing this part. So this is your water side flux or your convective flux. Your convective flux is equal to your diffusive flux, right? And in that diffusive flux we had minus dA23, that is diffusive constant and coefficient, and then we had this rho A2 node minus rho A2 infinity, or divide by not infinity to at some distance z. Here z is equal to 0. And then we have dz. Okay, so what it is saying that this one is 0. If we are assuming that this one is 0, it means whole term is will be equal to 0, is it? So if we are assuming that this rho A2 where z is equal to 0, so if this is the case, then this whole term diffusive flux will be equal to 0. But this is not the case. So the case is little tricky. So what we are assuming is that if whatever is so at the interface from the sediment side, if this A is moving to the interface, and whatever is going to that interface and is this crossing this water side, everything will be removed. So what we are saying that if everything is being removed, then this convective flux will be equal to zero, because what we are assuming is that everything that is coming from bottom to up will be removed by the flow in the water side. So that's how what we are saying is that your convective flux uh, is giving you the zero, and because of that, this boundary condition rho a2 z is equal to 0, time is equal to 0, this will be the condition. So it means the convective is much faster than the diffusion, and that's how we are assuming here we will have nothing at the convective side, because whatever is coming from the diffusion, it will be removed immediately, and that's how we are saying that this is equal to 0. I have explanation for this. So yeah, so this rho a2, that is the concentration of species A at the interface, is always 0. How it can possible? So this is at interface, that is z is equal to 0, chemical is arriving from sediment by diffusion, and we already know that this is your diffusion term, but the concentration at the interface is 0. Why this is 0? Because as soon as A is reaching to this interface, water will immediately remove it by the convective flow. So that's how we are saying it is equal to 0. And yeah, so physically it is not that we can't say that this is equal to 0, but just to simplify, just to make the equation simpler in the form, we are assuming it that convective flux, because everything whatever is coming from the diffusion, that is completely removed by the convective, and that's how, if it is completely removed, then this means diffusive flux will be equal to 0. So yeah, and one important thing is that this is your convective side, right? This is your convective side flux. So how it can be 0? So this will be 0 only when this will be approaching to the infinity. So this is your mass transfer coefficient. So it means whatever is going to the interface, the speed is faster that it will be removed. And how it will be removed? It means your mass transfer coefficient in the water side is very very high, and that's how what we are saying is that capital A2 3 approaching the infinity. So that's how, to keep rho A2z is equal to 0, the removal must be extremely fast. Okay, now coming to the another question. In the diffusion controlled case, the flux varies approximately as 1 by square root t, where t is time. What does this imply? Flux increases with time, flux is constant, flux decreases inversely with square root of time, flux becomes 0 instantly. I think this is simpler MCQ, because from the question only we can tell what should be the right answer. So as we already have talked about this, so this is your sediment part, and this is your water part, and your A is moving from sediment to water. So we have some flux here due to diffusion, and some flux here due to your convective term. And what we are saying is that here diffusion in the sediment side will vary with the time. So here diffusion at the sediment time, or flux at the sediment side, is the function of time t. So this n is inversely proportional to the square root of t. And we already have learned why this is the case, because um, at the interface we will have initially some concentration of A in the pore water, but as it will cross, there will be deficit, there will be decrease in the concentration near to the interface. And if we will not have sufficient concentration of your rho A2 to cross to the river, to the water side, then your flux will decrease. And that happened with the time, because initially we have enough concentration, but the over the time, as it is crossing the interface, your concentration will be decreased. If your concentration will be decreased, your flux will be decreased. Okay, so what we are saying, but how, if it is a function of time, then um, with the calculation, with the equation, what we learned is that, yeah, it is the function of time, and your flux will be decreased proportional to, inversely proportional to the square root of time. So this is your C is your right answer. Here again I'm telling the same thing. So you have, this is your flux at the sediment side, at the sediment side, or due to diffusion. So this is your flux minus d a32 um, um, d rho a2 by dz, and where z is equal to 0. Initially it is your flux, but as I told you, this is the function of time. Now what we are putting is, flux is the function of time, and if it is the function of time, then this will be your term. Here we have rho A20. Initially, this is the maximum concentration that we have initially, minus rho A2, z is equal to 0 at some time t. At some time t, your rho A2 will decrease, and this is difference, divide by, and because it is sediment, right? And sediment flux is now dependent on a lot of time, if it is if it is a function of time, because your concentration has to move or has to be transferred from bottom to up, then only there will be some flux. Okay, otherwise at the interface there will not any concentration, no flux will be happen. If it is moving from bottom to upper side of the sedimentation, there are a lot of factors that we have to consider. How it will move from your bottom to up, that depend on a lot of things, and that's how here we have this term, right? Square root of pi dA32 and t. And here also we have diffusivity term, and this diffusivity also have some a lot of factors that we already have considered. So if your surface concentration is 0, if this is 0, then your flux, that is the function of time, will be equal to, so what we are saying is that this part is now 0, this part is 0, then what will happen, this will be your equation at time, as a time function. And if we are putting this, if we are rearranging it, then what we are saying is that your flux is inversely proportional to the square root of t. Okay, so this is how we can derive the things. Okay, why is the maximum flux observed at time t is equal to 0? And you have four options. Suspended solids are maximum. Contaminant is already present at surface and only water side resistance applies. Background concentration is higher. Diffusion is fastest at depth. As I told you, uh, again, I'm drawing the same thing. I don't know how many times I will draw, but this is your sedimentation part and sediment part, and this is your water part, and your A is moving from here to here. Initially, what we are assuming is that the concentration of your rho A2 is equal everywhere, so it is uniform. It is uniform. So this row, and initially this is row A2 node. So everywhere the concentration of A is uniform at time t is equal to 0. So when we have time t is equal to 0, everywhere in the sediment part, this concentration of A2 will be your A2 node. Okay, so here at the interface also, the concentration is rho A2 node. Then it means at the interface already we have this concentration, and this concentration will move to the water side. Okay, this is the first thing. Second thing is that as this will move to this part, it means the concentration will be changed. Now let's say this is the concentration rho A2 dash near to the interface, and this is lower than these, which is at z approaching the infinity, which is lower. So this concentration has to move to the interface, and then it will cross. Okay, and then the flux will take time. Okay, so what we have learned is that with the time the flux will be decreased, because your rho A2 will decrease at the interface. But when time was 0, everywhere the concentration of your A was uniform in the sediment side, and that's how this was giving us the maximum flux. But with the time at the interface, flux will be less, and concentration will be less, and that's how flux will be reduced as the function of time. So your maximum flux is observed at t is equal to 0, because contaminant is already present at the interface. As I told you, here at the interface already at time is equal to 0, we have rho A2 node. We do not, there is no any kind of resistance in the sediment side. Just the resistance will be on the water side. But with the time, the concentration will be reduced in the sediment side, and that's how there will be more resistance from the sediment side also. And that's how flux will be reduced. But when time is equal to 0, we already have contaminant at the surface, and that's how this is giving us the maximum flux. But with the over the time, the concentration will be reduced at the interface, and because diffusion is slow, the concentration will be replaced, or the sufficient concentration will be after a long time, and that's how the flux will be reduced. But at flux will be 0 when we have t is equal to 0. Sorry, there will be maximum flux when time is equal to 0. So yeah, B is the right answer. Yeah, so this is again the explanation that initially at time is equal to t0, and at every z position from z0 to z is equal to z, or approaching the infinity, everywhere you have uniform concentration of A, and that is represented by rho A2 node. And at the interface also there will be the same concentration, and so this is your maximum concentration that you can have, and that's how this is giving you the maximum flux. But this will be reduced with the time, and that's how this flux will also be reduced. And that's how at time t is equal to 0, it is giving the maximum flux. So physically what we can say is the contaminant is already present right at the interface. It can immediate transfer into water. Only resistance is on the water side. As time will increase, surface concentration decrease due to removal. Diffusion will be from deeper layer become limiting, and that's how flux will reduce. So there is a maximum flux when time is equal to 0. Okay, then next question is, in the two resistance model, so sediment side resistance and the water side resistance, which statement is correct about resistance? Both resistance are constant. Sediment resistance is negligible. Water side resistance increases with time. Sediment resistance changes with time, while water side is often constant. We already have learned. I don't think that there should be any problem with this MCQ, because till now we have learned a lot about this resistance from sediment side and to the water side. So the D answer is the right one. That is sediment resistance change with the time. What we have learned is that, yeah, because here the flux is proportional to the square root, inversely proportional to the square root of time. We have learned, because there is a diffusion is slow, there will be less concentration with the time at the interface, and the concentration has to move from bottom to up, and this will take time. There will be the deficit of concentration at the interface, and that's how with the time there will be more resistance. Okay, but if we are going to the water side, this is not diffusion that is driving the flux. This is convective. This is due to the flow. This is due to the flow rate that we have. Okay, and here we do not have such depletion or something. Here it is driven by convective, and convective is very strong. Whatever resistance it will have, it will be the resistance will be the same. So that's why sediment resistance changes with time, while water side is often constant. Again, I'm showing you the same thing. So uh, we know that diffusion is fastest at the depth, but just leave that statement right now. Just see here, your concentration of A in the pore water is also the function of your distance and time in the sediment side, right? And so this can be expressed at rho A2 node 0, because it is the time of it is the function of your distance and time also, so these factors will come. Okay, and initially when it was not a function of time and function of distance, we have a normal formula, but if it is a function of your distance and time, then the formula will be changed. And we know that flux is given by your Fick's law. We already have learned that this is your uh, diffusion coefficient, and this is your change in the concentration with distance z from the interface. And if we are putting the things into this, uh, um, here we have partial differential equation. So this part will be, this is a lot, this came from this part, and that's how what we learned is that your flux, if it is a function of distance and time, then this will be a little complicated term. Okay, so this is your sediment side. um, and yeah, this is the function of distance and time, and that's how this will change over the time. But if we are talking about the water side, there is just conviction, and then there will be no any. So this will be constant. This is not dependent on distance and time. So that's how your diffusion is strongest near the surface because there is the largest gradient. Deeper region have weaker gradient. Diffusion effect propagates gradually downwards. We already have learned about these things, right? Okay, now coming to the different term, and that term is resuspension. This resuspension increases turbidity because I have four options here. Only dissolved contaminants are released, particles are removed permanently, contaminated sediment particles enter water, diffusion becomes faster. Deepa gave me C answer, that is sediment, contaminated sediment particle enter water. Yeah, so this is the right one. So yeah, C is the right answer. So the thing is that again I'm saying that we have sediment here and we have water, and this sediment are like these particles that we have, and in between we have pore water, and in the pore water we may have our contaminant A, but on this particle also we have contaminant A that is attached to this particle. So whenever there is resuspension, so these particles will go to your water side, right? Not just the contaminant that is moving to the water side, but this your sediment part is also going to your bulk water, and that's how this will increase the turbidity. So the first thing that you need to learn is what is resuspension. So resuspension is the sediment particle from the bed are lifted into the water column due to flow, due to waves, or due to some type of disturbances. And turbidity is the cloudiness of the water that depend on the amount of the suspended particles that we have. And this resuspension occur when your solid sediment particles will move from bed into water, and this particle also have some contaminants, and the number of suspended particle increases, and that's how turbidity will be increased. Okay, now what we are saying, we have wa3. So wa3 is the solid phase contaminant concentration that is independent of particle size. This can underestimate risk because large particles dominate contamination. Fine particles carry more contaminant and remain suspended longer. Dissolved phase dominate transport. Coarse particles move faster. If we are talking about the resuspension, and in the resuspension, what is happening is that from the bed, that we have bed under the water, the solid particle will move to the water side, right? So and so this is wa3. So wa3 is uh, your solid particle, and on solid particle you have your concentration A. If we are assuming that your solid phase contaminant concentration is independent of particle size, then it can increase the underestimate risk. Why? Because fine particle carry more contaminants, because the surface area for the fine particle is very high, and we know that we have Brownian motion. Because of this Brownian motion, that will remain suspended longer into the water, and that's how this will increase the resuspension. So the first thing, like if we have your solid phase contaminant concentration, okay, If we are calculating this contaminant concentration, we also have to consideration into the particle size. Okay, and that's how we can go to the resuspension and the turbidity part. So we have to take into consideration the particle size. I think I already have given the explanation for this, so I'm moving to the next part. After resuspension, desorption followed by volatilization leads to air pollution risk because contaminants directly become gaseous in sediment. Dissolved contaminant can evaporate from water. Turbidity converts solids to gas, and diffusion stops completely. If there is a resuspension, so resuspension means your solid sediments particle has been moved to the water part, right? If this is the case, and if there will be desorption followed by volatilization, then what will happen and why this is happening? So this is something that you have sediment, okay, and this sediment is moving to the water side. The particle of the sediment are moving to the water side. So in the water now we have sediment particles. Okay, and in the sediment particle attached are the contaminants. Now what we are saying is that there is a desorption. Desorption means we have a particle that is adsorbed on the solid particle. So if there is desorption, it means your solid particle will be detached from A. The solid particle will be detached from A. So now A is in the water. It is in direct contact with the water. It is now not attached with the solid particle, sediment solid particle. Then we told that this is followed by volatilization. A will be vaporized now because now it is not attached to the sediment. It is right now in the water, and if there is any turbulence or anything, so it will go and it will volatile, it will evaporate, and this A will now go to the air, and that's how it can increase the air pollution risk. Okay, now why? Because your dissolved contaminants, now your contaminant has been detached from your solid particle, so that will be dissolved in the water, and then dissolved contaminant will evaporate from the water. So this is how this can we may have risk of air pollution if there is a resuspension, because of resuspension will be followed by desorption will be followed by the volatilization. Then your contaminant A that we had in the bottom of, let's say, sea or river, will go to the air and will create the air pollution. So B answer is the right one. Okay, now we have a very complex term, but this complex term is saying that your flux of A in the pore water is the function of time t, and your flux has been defined by this long term. So, what if we are saying that we want to calculate our flux of A in the pore water when time is equal to 0? So, what will be your term? If we are saying the time is equal to 0, then what will be the value of your flux? Flux for the contaminant A that is in the pore water. So, this is something that if we have t is equal to 0, this will be 0. This will be 0. right? And we have this expansion. So if we have this expansion and this whole term is equal to 0, then this exp0 is nothing but 1. And this erfc, this is the error function, this is also 0, and this will also be 1. So this is 1, so we are crossing, this is 1, this is 1. So your term, that will be this much only. So if we are calculating our flux at time is equal to 0, then our equation is very simple. But if we are calculating the flux with the time or with the with the distance z or z, then your equation will be more complex, because we have to take into consideration distance, time, everything, right? So when time is equal to 0, the flux will be very simpler. That is, and this is nothing, we already have learned, right? The flux that is we have, so convective flux is equal to your diffusive flux, right? And in convective flux, what we have learned is Ka23. So this is your convective flux, Ka23, and we have learned rho A2 node minus rho A2 infinity in the water. So because in the water side, the concentration of A is equal to 0, right? Crossing the interface at the bulk side, bulk water side, the concentration of A is equal to 0, so we remove this. So that's how, this is just the term that we need to take into the consideration when time is equal to 0. So this is what is showing here, right? So that's how uh, B answer will be the right one. So yeah, this part will be 1. This part will also be 1. What will be the remaining one is the this one part. Yeah. Okay. Now, in the simplified diffusion controlled case, we have um, here we have flux of A in the pore water as a function of time t, and here we have rho A2 node, and this is your, because this is your diffusion type flux, and because this is the function of time, then we have expressed into some equation, and this equation is like this. So what we are saying, when time increases from t to 4t, the flux becomes what? I already have given the answer. So this is something, because this is 1 by t. So if it is 4t, and this 4 is nothing, 2 raised to power 2, and that's how this will be double. Also, this will be, so this will be removed by this one, and this will be 1 by 2. Is it? So this will be half. So B is the right answer. So I already have given this. So because this is written, this is your diffusion side flux, which is the function of time. And if it will be 4t, then if we are putting here 4t, and so yeah, if we are putting here 4t, so we can move it outside as a 1 by 2, and then this will be half. Okay, so the next question is, this is very important. Diffusivity or diffusion coefficient Da32, Da32 is equal to Da2 and epsilon 2 4 by 3, the porosity E2 doubles from 0.25 to 0.50 while Da2 stays constant. And you need to tell me the ratio of your Da32 new divided by Da32 old. So this is something Da32 new divided by Da3 old. And what we are saying, we are doubling this E2. We are doubling this E2. So this is Da2. This will be same epsilon 2 4 by 3 divide by, this is new one and this is old one. So this is Da2, and because here E2 has been doubled, right? E2 has been doubled. So this is 2 E2, um, or we can say this one. So this has been doubled 4 by 3. So now you need to tell the constant, the ratio, what will be the ratio. So this will be cancelled out. This will be cancelled out. So what we can say is that we have E2, that is old, E2 new 4 by 3, right? If we have E2 and if we are doubling this, 4 by 3, right? So this is how we can solve this. Let me show you the results so that so this will be 2 4 by 3. And how we can solve this? So we were here. So we were here. So we have, okay, the new one is at the upper side. So that the mistake that I did, because this is upper one. So here Da2 epsilon 2 4 by 3, that is new, divide by Da2 epsilon 4 by 3 2, that is older one. So older one is 0.25 and newer one is 0.50. So this means this will become 2, right? This will become 2. This has been cancelled out. So what will be remaining is this one and this one, and we already have calculated that this is 2. Then this will be 2 4 by 3, right? So this is how we can solve such kind of questions. And yeah, so what we did is we increased epsilon value, right? And epsilon value is showing us the porosity. So if we are increasing the epsilon value, we are increasing the porosity, and if porosity is increasing, then there will be less resistance, diffusion will be easier. And that's how, if we are doubling the porosity, your diffusion will be increased by 2 raised to power 4 by 3, not just by 2. Okay. The next term is, if you are calculating the overall resistance, that is ROV, the resistance will be the resistance from the water side and resistance from the sediment side. And if it is from the water side, then this is simply 1 by capital K A23. But if it is from the sediment side, because as I told you, the flux is dependent on the time, so this is square root of pi t divided by diffusivity, that is Ta32, multiplied by retardation factor, Ra32, which term increases with time? So if we have this overall resistance due to water side and due to the sediment side, so which term is increasing with the time? I think this is the simpler one. Which term is increasing with the time? So the term that will be increases with the time should have the time factor or the time function, or you can say the time variable it should have, right? So for the water side resistance, we have just 1 by capital K A23. We do not have the time variable in this. But in the resistance due to the sediment side has the term that have the variable T. It means your overall resistance will be increasing with the time in the sediment side. So the term that is increasing with the time is this one. Very simple. So initially resistance is low, we like we can easily transport it, but with the time, because the diffusion will penetrate deeper into the sediment, as I told you, there will be the depletion in the interface, and that's how the concentration gradient will be weakened and there will be transportation will be harder, and that's how sediment resistance will be more with the time. And that's how we can what we have seen is that this T is directly proportional to the square root of T is directly proportional to the overall resistance. Okay. Now, for the approximate, we already have learned that this overall resistance is due to the water side and due to the sediment side, which is the limiting value of overall resistance as T approaching 0. If T is 0, if T is 0, or if it is approaching 0 time, then what will be your overall resistance? We already have learned this. If time is equal to 0, then we already have concentration of A at the interface in the sediment side. So there is no any kind of resistance from the sediment if time is equal to 0. The all resistance that we will have from the water side. But over the time, because the concentration will be reduced near to the interface, that concentration has to move from bottom to up, then here there will be the resistance that will happen over the time in the resistance side, in the sediment side. So what we are saying is that if time is equal to 0, then if we are putting this is equal to 0, the whole term will be 0. It means the resistance from the sediment side will be 0 if time is approaching 0. And all the resistance will be from water side. But with the time, resistance from sediment side will be more and more as comparison to the resistance from the water side, and this term will be dominating. But with the time, but at time is equal to 0, sediment side resistance is 0, all the resistance is from the water side. Right, so this will be your equation, right? So KOV is equal to 1 by KA23, right? And if this will go up, so this will be KOV is equal to KA23. Is it? So all the resistance that we will have is from the water side at time is equal to 0. So the answer should be C. Yeah. So if this will be equal to 0, then what will be remaining is 1 by capital Ka23, and this will go up, and this will be is equal to capital Ka23. So what we are saying here, this is a very important part, the physical meaning. At time is equal to 0, the sediment resistance is negligible because we already have concentration of A at the interface. Only water side resistance exists. Overall mass transfer constant equal to water side constant. Okay. Again, we have for the boundary condition, uh, again, this is your convective flux. This is your convective flux. And this is your diffusive flux. This is your sediment side, and this is your water side flux. And what we are saying, that there is no any accumulation of contaminant A. That's how we are putting is equal to 0. Then what we are saying is that if this value will be equal to this value, the interface flux must be A is a negative infinity, 0, capital K A23, rho A20. The interface flux, it should be 0, right? Because if both terms will be equal and this will be 0, and 0 will multiply with this capital Ka23, it will become 0. So it means your convective flux in the water side will be 0, right? So it means here there was no any concentration difference between interface and bulk. So because this was your sediment side and this was your water side, and here at the interface you had the concentration rho A2 node, you can say right now node, because here Z is equal to 0. But um, rho A2 infinity will be at the water side here. So here also, if we have same concentration as we have concentration here, so if these are same concentration, it means there will no any flux that is moving. Okay, so there is a no any driving force for the transport, no gradient, no diffusion, so no flux. Okay. In the diffusion controlled approximation, sediment side resistance is R sediment is equal to square root of pi t divided by dA32 RA32 if this part dA32 RA23 becomes 4 times larger while the time remain unchanged. If we are this become 4 times, the new resistance is twice the old resistance, 4 times the old resistance, unchanged, half the old resistance. If your denominator becomes 4 times larger, then what will happen? What will be your new resistance? So your new resistance will be half of the old resistance, because this is 1 by 4 1 by 2, 2, 1 by 2. This will be 1 by 2, half, right? So new resistance will be half the old resistance. Okay, this is something different and new. So if the effective contaminant concentration, so the thing that you need to learn is that if you have sediment already have some contaminant on it, and the pore water also have some contaminant. So the concentration of your contaminant A will be concentration of A in the pore water plus concentration of A on the solid particle, right? Pore water. So, if we are calculating the effective contaminant concentration in water during resuspension is estimated by first calculating the mass of A, and this mass of A is equal to volume density, and this is WA3, where V2 is your water volume, rho 32 is your suspended solid concentration. Suspended, just see, this is suspended solid, and WA3 is your contaminant concentration of solid. Then the effective concentration, see if in water is, if we want to calculate the effective concentration, then what it will be. So this is something that you can say the mass of A is um, V2 rho 32 WA3, right? But what we need is effective concentration. So how we will calculate the effective concentration? So let me show you. Firstly, the answer will be because it is effective concentration, and concentration is mass by volume. So this is MA, that is your total mass that you have of that contaminant A by volume is equal to, so this will go down, and this will be equal to your concentration, in the suspended solid concentration multiplied by the contaminant concentration of the solid, right? So because the important part is, if you have pore water, so if you have this sediment, and in sediment if you have pore water, so what you have to see is first how much solid suspended you have in after the resuspension. So in the water, firstly this is the water, so in the water how much solid we have. So this is your suspended solid concentration. Within the solid, on the solid you have A, right? On the solid you have A, and that's why WA3 is the contaminant concentration on solid. So in the water you have solid, on the solid you have contaminant A. So that's how there is the multiplication. Rho 32, and this is WA3, that will be multiplied, and that's how this will give us uh, the concentration of A in particular volume, right? Or you can say mass in volume, so this will give us the concentration. So yeah, so effective concentration is your total contaminant mass divided by total water volume. So this will be MA divided by V2, and we already know that this will be equal to uh, V2 rho 32 WA3 divided by V2, right? So this is your mass, right? this is your mass that is taken from here, divide by total volume. So V2 will be cancelled, so this will be this one, right? Okay, very simple question. If you have rho 32, that is, so this is the mass of solid, the mass of, or the concentration of solid, or you can say the mass of solid per volume. So this is 1500 mg per liter, and on the solid, the mass of your contaminant is 80 mg per gram. If you need to calculate the effective contaminant concentration in water due to suspended solid is 12 mg per liter, 120 mg per liter, 1200 mg per liter, 1.2 mg per liter. Firstly, the concentration of solid is given, and then the concentration of contaminant on solid is given. And you need to calculate the contaminant concentration. You just need to multiply it to each other. But the important thing that you have to take into consideration is we have mg per liter here. So this is something 100 mg per liter multiply by 80 mg per gram. So we can't cross these two things together. We have to change this mg to first gram so that we can cancel gram to gram. So first, what we need to do is we have to convert this 15 mg per liter to 15 gram, 1500. So this we have to convert into gram per liter, and then we will multiply this with 80 mg per gram so that gram can cancel, and this can give us the mg per liter. Okay, and so that's how this will give us the concentration, effective concentration. This will be 120 mg per liter. Let me show you how. So first what you have to do is you have to change it to gram per liter. So this will be 1500 mg per liter will become 1.5 gram per liter, and then you have to multiply this. This will be cross, this will be cancel out, and what it will give us the 120 mg per liter. Okay, so the next question is, in the bioturbated layer, transport is modeled by this equation. I have given this equation. If this D bio A32 doubles and R bio A32 stays unchanged, the coefficient multiplying this partial differential equation we have for the rho A2 by Z square, that will become what? So what we are saying that if this is doubled, if this is same, then the coefficient will become what? So we are asking about this term only. So the coefficient will be doubled, right? If the numerator is getting doubled and if your denominator is unchanged, it means your whole coefficient will be doubled, is it? So the important thing that we need to learn is, what do you mean by bioturbated layer? So bioturbated is nothing but because of biological agent, for example worms, there may be some turbation, there may be some turbulent, you can say there may be some turbulent in the sediment side layers. So for example, if you have sediment side here, layer and you have water side layer. And because you have a lot of particles, solid particles you have. And if any let me draw, if any worm comes, if any worms comes, then this will create some space, let's say, in the sediment side. And this space can enhance the diffusion. So it means the transport that was just by the diffusion in the sediment side can be enhanced by the bioturbation, right? But just you need to keep in mind that diffusivity will be different. Diffusivity due to bioturbation will be different from the normal diffusivity. And again, the retardation factor will also be different from that. So it will be twice its original because we are increasing the numerator but not denominator, and that's how the ratio will give us the double. Okay, so again, I'm giving the definition of this bioturbation. So this is nothing but the mixing of sediments by living organism. This organism disturb and rework the sediment, causing particle and dissolved chemicals to move more rapidly than by molecular diffusion alone. So that's how this is the change in concentration per time. We can also write it in the form of biodiffusion also. So, and so this is bioturbation enhanced diffusion coefficient that we are putting, retardation factor in bioturbated sediment, and this is your gradient. So we can write such term also if we have bioturbation factor. Okay, and the next question is, at the interface z is equal to z1. So this z1 is nothing but this is where bioturbation will start. So is equal to z1 between bioturbated layer and underlying sediment. Continuity of diffusive flux requires what? So it is something that in the sediment side only, this is water side, but this is sediment side. And within sediment side, let's say, so we have z is equal to 0. So we have different layers, right? Let's say we have different layer, and z will be change. Z will approach here the infinity. And let's say this is z1, z2, z3, z4 or something. So let's say at z1, or let's say at z1 to z2, this was your where bioturbation happened, right? This is, let's say, this is the place where bioturbation happened, and this is the place where normal diffusion happened, right? So what we have to do is the flux due to this layer should be equal to flux due to normal diffusion, because what we are saying is that there is no accumulation of your contaminant. So whatever flux we have by the bioturbed layer will be equal to whatever flux we have from the diffusive layer, and that's how we are putting it equal to each other. So this is your flux due to bioturbed layer, and this is the flux at your normal diffusive layer. And because there is no any accumulation, then this has to be equal to 0. Oh sorry, this has to be equal to each other. So B answer will be the right one. So is when two layers have different transport property, the flux leaving one side must equal the flux entering the other side. Equal diffusivity are not required, but equal flux is required, and that's why we are keeping equal to each other. Okay, if we have a top bioturbated layer that has the thickness Z1, and transport through that layer is much faster than in the lower sediment, then after a long time the overall resist release rate will mainly be controlled by diffusion from deeper non-bioturbated layer, feeding rate of worms only, dissolved oxygen in the water column only, desorption from the atmosphere. So see, if this is your interface, you have water and you have sediment part here, and in the sediment part at different distance you may have one layer, you may have a bioturbated layer, and another layer may be your diffusive layer. Okay, so what it is saying that if the top bioturbated layer has the thickness Z1, so this is your Z is equal to 0, and let's say this is Z is equal to C1, and this is your bioturbated layer. This is your bioturbated layer, and the layer through that the transport through that layer is much faster than the lower sediment. So let's say this hole is your Z is equal to Z1, and below one is your this one is your lower sediment, and where there is the diffusion, there is just the diffusion but not the bioturbated layer. So so it means here the diffusion will be faster, right? Here the diffusion will be faster and here diffusion will be slower. So what it is saying that after a long time, the overall release rate, we need to move from here to here. After a long time, the release rate will be mainly controlled by which layer? Always, the release rate will be dependent on the layer, which is the slowest layer, right? Because this is faster. Here the transport will be faster, that will take no time. But the important part is the below one, the sediment diffusion part, where we do not have bioturbated layer, and here whatever diffusion time it will take, that that is the main time, because this is taking no time. So let's say I'm saying that the upper layer is just taking 5 seconds, but the lower side is taking, let's say, 4 hours. So the release rate will depend on this 4 hour, 4 hour, not just on the 5 second. So it means the slowest layer is driving the overall release rate. So it means it is controlled by diffusion from deeper non-bioturbated layer. So A will be your right answer. This is shown by this one, as we can see. So overall resistance will be due to your bioturbated layer and due to your sediment. And for bioturbated, the resistance is given. Resistance for sediment layer is also given. And because transport in the top layer is much faster, it means diffusivity is much faster for bioturbated layer. It means resistance due to sediment layer, because it is inversely proportional. So it means your resistance due to your sediment layer that is below to the bioturbated layer will determine the resistance. There will be more resistance. More resistance means overall resistance will be controlled by this more resistant diffusion layer, right? Yeah. Okay. We have considered the advection diffusion reaction form. So what we are saying, changing the concentration with the time, concentration of A in the pore water is dependent on a lot of things. The first thing is how it is transporting to the bulk water. Okay, so this is your flux. Then there may be some velocity, some convection or advection, you can say, some advection. For example, in the groundwater, the water is moving in the sediment also. Okay, so this is something advection. Horizontally, there is a movement of the water. So the change in the concentration of A with the time is dependent on transfer coefficient, or how it is transferring, and this transfer due to the diffusion. So this is diffusion part, transfer due to advection, and there may be some reaction, that is also removing the concentration, or that is also decreasing the concentration of your uh, rho A2. Okay, so it means the change in the concentration of a contaminant A is depend on diffusion. The first term is showing the diffusion, the second term is showing the advection, and third term is showing the reaction. So if I'm saying velocity is equal to zero, what water do not have any velocity, the reaction rate constant is also zero, then this reduced to what? Pure advection, pure reaction, diffusion with the retardation only, steady state mass transfer. As I told you, this is showing us the advection, right? And if this will be zero, the whole term will be equal to zero. So there will be no advection, right? This is your reaction term. So the change in the concentration with time dependent on the decay rate constant, let's say. So if reaction rate is zero, then this reaction will also be zero. It means your change in concentration of this A2 will depend on your diffusion. And because it is the function of time, then there will be some retardation also. So if these two will become zero, then your change in the concentration with time will depend on your diffusion with retardation only. So C answer will be the right one. Yeah, this will be become the first term only. Now, in the same equation that I showed you, if RA32 increases while DA32V and the reaction rate constant remain fixed, what we are increasing is just RA32, then the magnitude of diffusion, advection, and the reaction terms will become larger, zero, unchanged, smaller. The magnitude of diffusion, advection, reaction term will become. So this is RA32. Let me show you. This is your RA32. And it is saying that this RA32 is increasing. If this is increasing, what will happen to this one? Obviously, it will become smaller. Is it? Or in the question is, then the magnitude of diffusion, advection, and reaction term will become smaller. The diffusion will be smaller because the retardation is higher, advection, and this is the reaction term. Okay, the next question is, if we have methane bubble, so this is very interesting part that we have. So this is again sediment and this is water, and in the sediment we have methane. So let's say this is methane, and methane create bubble, and that bubble create channel in the sediment, and average upward pore water velocity become non-zero. It means the bubble that has been created in the sediment side is giving the velocity it to transfer. So this is something we learned, that sediment side we have just the diffusion, right? And because of the diffusion there is a flux. What we are saying here is that we have methane bubble, and methane bubble is having some velocity. And if there is any velocity, it means we will have diffusion, plus due to velocity also there will be the change in concentration. With time there will be movement due to the velocity also, which newly term appear as the direct mathematical signature of advection. So it means if the change in concentration with time in the sediment is also depend on the advection, is also depend on the velocity, then which term will appear from this term? Which term will become more important if such is the case? Because you know that diffusion is slower, so if there is any movement, and if that movement is due to the bubble and that bubble is creating the channel, it means it is having some velocity, then this term, advection term, will become more important for us. And this is the signature of advection because it has the velocity term, is it? So that's how c is the term that has the signature of velocity. Yeah, so advection is represented by the first special derivative term multiplied by velocity. And so this will show you the bulk upward movement that is caused by bubble driven motion. Okay, very simple question. If you have diffusivity or diffusivity constant due to bioturbation and normal diffusivity we have, so the range is given. The diffusivity due to bioturbation layer is 9 multiplied by 10 raised to power minus 10, and normal diffusivity we have is 1 multiplied by 10 raised to power minus 10 meter square per second. Then the bioturbated layer diffusivity is 3 time larger, 9 time larger, 81 time larger, 9 time larger, smaller, sorry. Normally we just need to get the ratio, diffusivity ratio, bio, and this is the normal diffusivity. So this is 9 multiplied by 10 raised to power minus 10, 1 multiplied by 10 raised to power minus 10. This will be cancelled out. This will be 9 times. It's larger. So if diffusivity constant of due to bioturbation uh, is larger, then obviously the diffusivity will be larger, 9 times larger. Yeah. Okay, very important question now. Why can DOC facilitated transport move contaminant upward faster than ordinary dissolved phase diffusion, even when the contaminant itself is strongly soaked? So this is something that you have sediment, and sediment have organic carbon. Okay, sediment have organic carbon. Um, that is giving you the facilitated transport that will move contaminant upward faster than the ordinary dissolved phase diffusion. If you have contaminant that is on the solid, and that solid have organic part, let's say clay, organic carbon, so the transportation will be much faster than you have ordinary dissolved phase diffusion. So if you have contaminant in the pore water, so there will be diffusion, right? So the thing is, your contaminant can be present in the pore water, so there will be diffusion, and that's how there will be transportation. Your contaminant will be on the solid part, and if that solid part have that that is organic rich, and that may also facilitate some movement of your contaminant, even though the contaminant itself is strongly soaked. Why uh, why this part is moving your contaminant faster than your ordinary dissolved phase diffusion? Because colloid carry the contaminant while colloid themselves diffuses. Because Ra32 become exactly zero, become because reaction term vanish in all sediment, because oxygen concentration is always constant in depth. So here the thing is, you have a solid, and on that solid you have contaminant, and if this solid is colloidal in nature, that will carry the contaminant, and the movement is faster than the water, pore water, that itself has some contaminant, and it will diffuse. That's how it will transport. But if you have colloid can move, right? And that's how there is the faster upward movement due to DOC. So A will be your right answer. So this is something. And DOC is dissolved organic carbon or colloid. So normally contaminant transport in the pore water, and that is driven by the diffusion. We have learnt about this. And here, Ra3 is very large for strongly soaked contaminant, and that's how transportation will become very slower. So it means your dissolved phase diffusion is limited. But if we have dissolved organic carbon colloid, so your contaminant is attaching to your mobile colloid, right? If so the flux, total flux will be the flux due to dissolve and flux due to the colloid movement. And if your colloid movement is more, then it means the total flux will be determined by this colloid movement, and that's how this is more faster. Okay. Now we are moving to soil water exchange. Till now, we were talking about sediment water, right? Sediment water transport. But now we are moving to the soil air exchange. So we have soil. Soil can be okay. So there is a different case. First, we are replacing water to air. It is okay, but we are replacing sediment to soil, and because we know that sediment is saturated with the water, right? But soil can be wet, soil can be damp, soil can be dry. So there will be different scenario for soil air exchange. So if we have soil air exchange, air exchange, the governing diffusion equation is written here. If Da31 doubles, if this is getting double, and Ra31 this is remain unchanged, the coefficient that is multiplying with this will become what? Then obviously it will be doubled, right? Because the numerator is getting doubled, so this will get doubled. Okay. Now, in soil air effective diffusion, so we have coefficient, and this coefficient is now Da31. 3 is for the soil, 1 is for the air. Okay, so this diffusion coefficient is related to Da1, and here we have porosity of your soil. So porosity, epsilon A 10 by 3 divided by epsilon 2 T, that is the effective porosity is driven by porosity in the water, in the air, and porosity in the water, right? So if moisture is negligible, if this part is zero, if there is a no moisture, then porosity, this part will become zero. So epsilon T is equal to epsilon 1. So this reduced to, so if we are removing this E2 term, then what will be your Da31? So it is something that you have epsilon 1 10 raised to power 3 uh, e1 raised to power 10 by 3, and then this one is, if this is again e1, because we are neglecting that epsilon 2, and this will be 2, so this will be e epsilon 1 10 raised to power e raised to power 10 by 3 minus 2, right? So, and then here it will be dA1 is equal to dA31, right? So you just need to calculate this part, and that's how this will give you the answer. And this answer will be, I think, this one, A1. You can calculate, you can see how we can calculate. Yeah, so this is 10 by 3 minus 2, and this will give us the 4 by 3. Last question I think we will solve, and then we can go for the dinner. We have retardation factor. This is Ra31 for vapor transport in soil. Okay, is written as this one. If we will increase this K star A31, while even even this is epsilon 1, this is epsilon 1 and rho 31 remain constant, then this Ra31 will, so if we are increasing this one, then this retardation factor will also increase, right? Because this is directly proportional. So D1 is the right one answer. So we stop here, and we will pick more question on our last live session that will happen on Tuesday. And till then, happy reading. And yeah, you can go for your dinner, and good night. Thank you so much.